Hey, this is Mr. Reed, and this is Calculus, and we are in differentiation, or what we call derivatives. And today will be one of the easiest videos that you've ever done. It's called the power rule for derivatives, and it will make everything make sense. So what we've been doing, we've been taking a look at the instantaneous rate of change. We've been taking a look at the average rate of change. We've been taking a look at the limit process, all these different things. So I'm going to kind of group together everything we've been taking a look at. Let's say we have this point at 1, 2, and we want to know what's the instantaneous rate of change, the slope, at 1, 2. Well, we're going to look at a different point, aren't we? And we're going to take a look at its rise divided by run. Now, what's great about this linear function is it's linear, which means the rate of change is not changing. I can take any 2 points, and what do you know? The rate of change is equal to 4. And we call that the slope, or the derivative, or the instantaneous rate of change at any single point in time. Now, this is really easy because you know the slope is 4. You know we have y equals mx plus b. You know that this 4 stands for the slope. It's always stood for the slope when you were in middle school, all the way through high school. And so the rate of change is not really changing. It's continuing to stay consistent throughout this function. Okay? Well, linear functions are really easy. What about a function like this? What about one that's curved, right? There's the problem. What is the, let's take this point right here. Let's take this point right here at 2, 2. What's the instantaneous rate of change? Well, what have we done in the last few videos? We've taken a look at what's called the limit process, aren't we? We've taken a look at like a point C. I'm going to, at some point C. And it's f of c, its y value. And we've taken a look at what is the slope between this. What's the, what we call the secant line. And so we've been taking a look at this f of c, whatever this point is, minus 2 over c minus 2. And we've been trying to get this point c really close to 2, aren't we? We're taking the limit as c approaches 2. And that has given me the slope, or the instantaneous rate of change. Now, I don't know about you, that ends up being a lot of work, isn't it? Because we're going to try a point like, in my function, like 2.1 or 2.001 or 2.0001, and we keep plugging in my function. We got to do the slope. We end up finding the slope. Now, it's not bad. It's not bad to put 2.1 into this function, or 2.001. It's not too bad. But what about when your function looks like this? 3x to the 5th plus 4x squared minus 3x minus 1. That is, and we're trying to find out what's the slope of the tangent line at this point right here. Well, that takes a little bit more work, doesn't it? That is going to be a little bit more tedious. And so what the amazing Gottfried Leibniz did, not Isaac Newton, but Leibniz, came up with what's called the power rule, which takes that entire slope formula, that definition of the derivative, and every calculus student is peeling off the road to do the power rule because it is easy peasy lemon squeezy. And to take the derivative, to find the instantaneous rate of change, the easiest thing is this. You take your power. Whatever the power is, you multiply it out, and you take that power and you subtract it from 1. It goes down. And that is what's called the derivative. So let me give you an example. Here I have f of x equals 3x squared. So how do I find the derivative of this? I'm going to take this power, this 2, I'm going to multiply it out. So 2 times 3 is 6. And the x, this 2, goes down 1 value to the first power. So the derivative of that is 6x. Now let's take a look at the next one right here. Let's take a look at the next one. Here we have y equals 5. Well, remember, this is really 5x to the 0 power, isn't it? Why? Because the 0 power that equals 1. So that's why it's not even there. So when we multiply out, 0 times 5 is 0. So any constant like 5 or 12 or 13, the derivative is equal to 0. So let's go to the next one. The next one, we have y equals 5x plus 6. So what is the derivative, y prime, of this? Well, remember that this is x to the first power. Really, that's x to the first power. So 1 times 5 is 5. That x goes down to x to the 0 power, so it's just 5. And remember, any constant equals 0. So that's the derivative. So if we come back to our examples, let's take a look at this example. What's the derivative of this? This is really 4x to the first power, so 1 times 4 is 4. That x becomes 0 power. That is the derivative, or the slope, or the instantaneous rate of change, is 4. So that's how we got from this linear function down to using the power rule. Okay, you were using the power rule, you didn't even know. So let's take a look at something like this. What's the derivative of x squared minus 2? We multiply this 2 out front, so we get 2x that goes down to the first power. Any constant is 0. There's your derivative right there. Okay, how do we find the derivative of this? We're going to take our power rule. 5 times 3 is 15. X goes down to the fourth power, plus 2 times 4 is 8. X goes down to the first power. This 3x becomes 3. Any constant is 0. And so there's your derivative. And so that is able to find the instantaneous rate of change at any single point. If you take this back to kind of physics and gravity, remember, here, what's the position that this person throws this ball? It's 0. It's going to come back in, let's say, 10 seconds at 0 again. And remember, what did that look like in physics? That looked like it went all the way up in what's called a parabola. That's not a great parabola right there. Let's do it a little bit better. That's a little bit better. There's my ugly parabola. You're like, Aiton, the last one looked even better. And so, yeah, I don't care. So there we go. It's a beautiful parabola. You can see this is the maximum height, the maximum position that it was at. It was at 2 meters up, okay? And this is what, if you remember, a position time graph looked like, because as soon as it left this person's hand in physics, remember, all that's working on it is gravity. Now think about, how did we go from one graph to the next? We took a look at what's called the slope, or we will call it the derivative, the change over the time, the derivative. And so the derivative is showing the instantaneous rates of change. And so here, take a look at this, is a positive slope. If we take a look at the tangent line, here is a positive slope, but it's a little bit less. Here's a positive slope, but it's a little bit less. Here is a 0 slope, isn't it? So that, if you remember, when we translated into my function right here, we had a positive slope, we had a positive value, then we had a less positive value, less positive value, less positive value. It was like a linear, negative linear slope, and then you can see on the back side, my slopes end up being negative, 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 negative. So that was taking a look at my instantaneous rate of change, And how did we go from one graph, from the velocity time graph to an acceleration time graph? We took the slope, or what we will call the derivative. And so look at the value right here. Is that derivative? It's a linear function. It's always negative, which means it will be a constant negative acceleration. And so let's take a look at what this function would look like. Okay, if you remember, we had my height, my position, my height was equal to 1/2 gt squared, if you remember that. And so when we took a look at my change of my height, my derivative, let's use my power rule. So I'm going to multiply by 2. 2 times 1/2 is 1, and we ended up getting gt. If you remember my formula for velocity, my velocity equals velocity initial plus acceleration times time, gravity times time. That was exactly the derivative of what we got. Now let's take the derivative of that. This is t to the first power, so I'm going to multiply out that equals 1g, and that t goes down to 0. So the derivative of velocity, which we call acceleration, is equal to gravity, which was negative 10 meters per second squared. So you can see how this still, all of our physics, ends up making sense using our calculus. So let's do just a few more problems, okay? This problem right here, we have f prime of x is equal to, we multiply out, we have 8x plus 3. Let's take a look at this one right here. My y prime equals, we're going to use my power rule, 24x squared plus 8x minus 3. And look at this last one. It's x to the 1/2 power. So again, we're going to use the power rule. 1/2 times 4 is 2. This 1/2 goes down 1. What's 1/2 subtracted from 1? That's negative 1/2. And my last function right here for an example, when we have negative, we just treat it the exact same way. Negative 2 times 2 is negative 4. X, negative 2 goes down 1 to become negative 3. Plus 8x minus 8. And so this is what's called a derivative, or finding the instantaneous rate of change of any function. The power rule for derivatives.